Good morning, everyone. I'll give everyone a few more minutes to get joined in, and then we'll start with our conference and welcome. Okay, we'll get started. Good morning, everyone. Thank you for taking the time to attend our 2020 inaugural Extreme Environments Conference for UTSA's newly established NASA Murrow Center for Advanced Measurements in Extreme Environments, which we call in short, CAME. My name is Carla Kidd, and I manage the day-to-day business operations of the center. I will also serve as your guide throughout the day of scheduled activities. I would like to start by providing a few details regarding the scheduled activities for our morning session. As listed in the agenda, our morning session will consist of the welcome from our center director, Dr. Hongji Shi, the presentation from our guest speaker, Dr. Siva Prasad Ghojanini from the University of Alabama, who also serves as our chair of the External Advisory Committee. To conclude the morning session, we will have research presentations from our Alamo College's student interns who were mentored for 10 weeks this summer by CAMI PIs and CAMI affiliated faculty. After the presentations, we will break for lunch and return for the afternoon session through the provided Zoom link in the agenda and meeting invite. I ask that you please mute your audio during speakers' presentations. If you have any questions or comments, please be sure to drop those in the chat. I will present those questions to the speaker if time allows. If we are limited with time to respond to questions, I ask that the students' PIs assist in responding to those questions while the student is presenting. The student will also have the opportunity to respond to questions in the chat once they finish their presentation. Now I would like to introduce our Center Director, Dr. Hongji Xi, who also serves as our chair for the Department of Geological Sciences. Since 1993, Dr. Xi's primary research interests have been focused on remote sensing and geographic information systems, GIS technologies, theories, and applications. His technical skills include expertise in uses of various image processing software and GIS tools. He has strong experiences in computer software development and GIS programming, and is particularly interested in interdisciplinary research by integrating remote sensing, GIS, field measurement in geology, the Earth and Mars, agriculture, surface hydrology, terrestrial ecosystems, hydrometeorology, urban development, cryosphere, and environmental studies. His technical expertise has allowed him to approach many research questions in regards to spatial temporal patterns and processes through quantitative analysis and modeling. Dr. Xi, I will turn it over to you now. Thank you.
Okay, thank you very much, Carla, for the introduction. Let me show the PPT, few slides. Yeah, okay. Okay, able to see this? Okay, so welcome everybody. Thank you for joining this conference virtually. I'm going to talk a little bit about the CAMI, which is the NASA Center for Advanced Measurements in Extreme Environment. So our vision of this center is to build a sustainable source of diverse, highly trained research to aid the NASA workforce in the fields of Earth system sciences, remote sensing technologies, computational flow dynamics, and experiment flow mechanics. So our center is managed by 6 persons, so 5 PIs, and also our program manager, Carla Kidd. So she manages the day-to-day activity of the center. Okay, so this center, you can see we have lots of partners, including the partners from the university, College of Science, College of Engineering, and also partner from NASA Research Center. We have Goddard Space Flight Center, JPL, and Langley Research Center. We also have some partner in the local and national research or foundations like Southwest Research Institute and National Ice Center Foundation, Texas Space Grant Consortium. We also have 3 university partners, including the Alamo College here in San Antonio, and University of Colorado Boulder, and University of California, Los Angeles. So the center of this figure you can see is education outreach, all the way from K-12 to postdoc. So we train our students, and we also send our students into NASA centers for internship, to CU and the UCLA for internship, and we also host the Alamo College student to UTSA for internship, And we also just finished our high school camp in this summer, and also teaching workshop. You can see all of these activities this year, unfortunately, is through online. But I know many students and our teachers, they actually also learned a lot, even though in this difficult time. So this table show you in the next 3 years, our training and education, how many students we will support, 64 students and 30 science teachers. And beyond the 3 years, we hope to continue to 5 year and the next 10 years. So we will build, we'll educate a massive, a bigger group of science, technology people, students, and they can serve and meet the national needs for science technology, especially the NASA workforce. So here is a research map, show what we are doing. So what do we mean extreme environment? So we mean the atmosphere, the polar region, the ocean, and even the little space and the deep space. So we use advanced measurement such as satellite remote sensing, ship-based observation, airborne drone, sea glide observation, laboratory measurement, and the supersonic experiment. So we use modeling simulation, big data technology to connect this measurement to this extreme environment. So we try to understand all of these processes and to predict the future change, especially in this current global warming situation. So here I go really quickly, our research, research focus area. One is aerodynamic, one is atmospheric science and extreme events, the Gulf of Mexico and the polar ocean, and the polar sea ice and the sea level rise, and the modeling simulation, the big data. So today, our student will showcase what they learned, what they studied on all of these 5 different focus areas. So I hope you will enjoy today's presentation, and you will encourage our students to continue the good work and to be able to enter into our future NASA and national STEAM workforce. So with that, I'm going to actually introduce our keynote speaker today, which is Dr. Hassar Gojnini. He's a professor in the University of Alabama. So he's in the Department of Electrical Engineering and Computer Engineering, and also Department of Aerospace Engineering and Mechanicals. So he's currently also a founding director of the Remote Sensing Center at the University of Alabama just a few years ago. Before he came to University of Alabama, he was a distinguished professor in University, Kansas. He was also a founding director for NSF Center, Science Technology Center, named Center for Remote Sensing of Ice Sheet. So he developed concepts and the early version of all radars flown as part of the NASA IceBridge mission for the ice sheet. So our department actually have one radar sensor built by their center, and we actually use lots of their data for our research from the IceBridge mission. So he has participated also a field trip in the Arctic and Antarctica, and also the many papers and the technical report. So his kind of research interest include application of radar to remote sensing of polar ice sheet, sea ice, ocean, atmosphere, and land. So he's also a fellow for IEEE and also member of many agent professional organization. And he's like Carla mentioned, he's also the chair of the CHEMI External Advisory Board. So his talk today will be the ultra wideband MIMO radar for mapping lava tube. So give the floor to Dr. Giorginini. Let me see. Let me close my window.
Can you see? Can you
Yes.
see my screen?
Yeah, see, this is not in the show mode yet.
Pardon? Oh, yeah. I'll put that on, but I just wanted to see if you guys see the screen.
Okay.
Okay.
Yeah.
Anju,
Yes.
thank you very much for the kind introduction and also inviting me to give the keynote talk. And I thought since you guys are dealing with extreme environments, so I thought it would be good to talk about mapping of the lava tubes. So this is a concept at this stage, and also there was some work done. So I'm going to go through some of the requirements, why we want to map it, and talk about how we can meet with those requirements from radars and what the radar characteristics should be to meet those requirements, and then take you to the concept of MIMO radars. And actually, there's a lot of people's work going into this presentation, and I want to acknowledge their work. I can't list everybody, and there was a lot of graduate students at Kansas, at Alabama that contributed to that, and also a lot of my colleagues, both institutions. My talk is going to be, I'm going to see if I can get the laser pointer. Okay, so I'm going to just briefly introduce why we want to do this and provide some background information, such as requirements from mapping lava tubes with radars, and then talk about what is an ultra-wideband radar and what are the developments in ultra-wideband antennas that's going to let us do what we could not do before, and address each radar requirement with examples from a lot of the ICE work that I was involved with, and present the MIMO concept and summarize with the conclusions on the potential for this. You know, lava tubes are considered potential source for human lunar exploration. And here are some images of the lava tubes on the moon. It is considered to be a home for humans so that they are protected from cosmic radiation and micrometeorites. And as you know that moon is supposed to be a base from which they're going to launch exploration of the Mars and other planets. And also lava tubes may contain water, other mineral sources to support human exploration of the planets. And gravity and radar data, and also some of the optical data, do indicate there are lava tubes, the presence of lava tubes on the moon. And I think we need both satellite and surface-based radars to map both shallow and deeper lava tubes. To do that, radars must have these following characteristics, especially to look at the shallow tubes, which are the ones that you're looking for human habitation. Find range resolution of 1 meter or better. Right now, there's nothing that exists with those characteristics that is going to the moon. High sensitivity to detect very weak echoes from the bottom and the top of the lava tube that could be masked by what is known as the surface clutter. I will show you what that surface clutter is in a few minutes. And the radars must have what is known as the area processing capability to determine where this signal is coming from. Again, I will explain why you want to do that. And you also want to reduce what is known as the cross-track. Clutter is any signal that masks your signal of desired signal. So that's why we call that clutter, and improve the along track resolution also. And SAR processing to obtain fine resolution in the along track direction. This should not be there, but this is basically This gives you cross-track, this gives you a long-track resolution, so you have fine resolution in both dimensions. And you also want a 3D imaging capability. You want to look through the surface, and also you want to have fine resolution to determine the extent and the extent of its tube. The MIMO means multiple input, multiple output. UWB means ultra wideband radars. Multiple input, multiple output. The concept has been around for many years. It's not new. I think it provides better angular resolution, but much of the early work was done for military applications because of the cost and the resources availability. And what happened in recent times is the radars are becoming a part of every automobile. And this concept is revived to incorporate into our automobiles today and for tomorrow. And this is to mainly obtain a better angular resolution so you can resolve the small objects on the highways, including humans. And the advances in RF and digital technologies are enabling this development of innovative radars with very fine angular resolution. What happens with a MIMO radar is there are N transmitters, M receivers. It's like almost sampling digitally, like a digital signal, but you're doing it spatially here. And you can do this by sequential transmission at one transmitter at a time and collecting data from all receivers, or you can actually do that all at one time with complementary coded signals like what we use in our cell phones today. And when you have N transmitter, M receivers, you get N times M minus 1 times the D. D is the spacing between the array. So you can synthesize a very large virtual array. And so that is what MIMO radar and virtual arrays mean. And I used to use this quote. Once I learned about Ford's racial comments, I did not use that much, but I've learned recently that everybody has made those sort of comments, so I started again reusing that quote. As Ford said, he said this. He was given a lot of credit for the automotive production, all those things, and really revolutionizing the automotive production. And actually he said that I invented nothing new. I simply assembled into a car the discovery of many other men behind whom there were centuries of work. Had I worked 50 or 10 or 5 years before, I would have failed. So it is with every new thing, progress happens when all factors that make for it are ready, and that is inevitable. To teach comparatively a few men are responsible for the greatest steps of mankind is the worst sort of nonsense. Again, it's the same thing with the MIMO radars, or some of the advances we are seeing in the radar. I think a lot of things are coming together today to let us do a lot of innovative stuff. Ultra wideband system means actually the bandwidth by FCC definition. Bandwidth has to exceed about 500 megahertz, or the fractional bandwidth with respect to the center frequency has to be about 20% or greater. So any radar that satisfies this criteria is considered ultra wideband radar. In my view, ultra wideband radar coupled with the advances in antenna arrays and unmanned aircraft systems or drones have a great potential to make significant contribution to remote sensing of distant planets. You don't have to have UAS for the distant planets. You can do that on satellites. And for the earth sciences, they can contribute to snow, soil moisture, ice bathymetry of rivers, and river flow. And also, as I said, this can be implemented from small sat sites in the future for the planetary as well as for the earth sciences. So that's what the definition of MIMO and ultra wideband radars are. And I also want to point out one thing that is letting us be able to do this is excellent development in the antennas. Today, through innovative techniques, what is known as the tightly coupled arrays, and using the CAD tools, people have come up with very, very broadband antennas with decent efficiencies. So you can see this is an antenna only 1.5 meters, 1.4 meters. It operates all the way from almost 100 megahertz to close to 2000 megahertz. That's ultra wideband. And in fact, you can push it down to as low as 40 or 50 megahertz to as high as 400 to 500 megahertz. If you change the dimensions, redesign this. This was basically given to justify some work. So mapping of the lava tubes, I stated earlier the requirements. And now I'm going to show you how each of these requirements can be met with the radars today and why that requirement is necessary. One of the things is radars must have a fine resolution of 1 meter or better to look at the shallow tubes that are really useful for human habitation. So here is an example I show, the need for a bandwidth and resolution. These are data that are collected on ice in Antarctica. We have similar results in Greenland. I didn't want to overload the presentation, so I didn't include them. But you can see these are mapping buried crevasses. And these radars are operating at 2 to 8 gigahertz, and today 2 to 18 gigahertz. You can see that you're mapping these crevasses extremely well all the way from onset to the upstream. So, if it's not for the resolution that is provided by that, what is known as the snow radar, that's the radar actually UT San Antonio has. Steve Ackley asked us to develop the radar and provided the funding. We developed and delivered it to him. So this is thrown on an aircraft actually, on the DC-8, and you're able to map all of these crevasses because you have the resolution associated with the bandwidth. And here is another example where the resolution becomes extremely important to do that. We developed a radar that operates with 60 megahertz bandwidth, which is this side of the images. We also developed a radar that has almost 300 megahertz bandwidth. Because of some amplifiers, we only operated it about 160 megahertz bandwidth last year in Greenland. This is the antenna array, and this is the signal of one of the lines here. As you can see there, as you go deeper into the ice, or even if this is at the top of the ice, and this is as you go into deeper to almost 2.5, 2.3 kilometers deep. And here, as you can see this fine resolution lets you map these internal layers with much better resolution. Very similar to that when you're trying to map the lava tubes, both the top and the bottom, and its structure. And again, you can see as you go deeper, this fine resolution provides much more details. Here it's all smeared. As you go here, actually you can't see some of this here at the deeper, whereas with the fine resolution radar, you can see those things. So those two cases, I show why bandwidth is important, why ultra wideband provides the necessary resolution or that satisfies the requirement. Another thing is you need a high sensitivity to detect very weak echoes from the top and the bottom of the lava tube. So that's what I'm going to show next. So you can see that one of the things we did in Alabama is there is something called a Mills Cross, which was developed for radio astronomy. We took that concept, developed a radar that has a T-type antenna pattern. This is your transmit array. This is your receive array. And you see, this is the original Mills Cross. We modified this in 2019. This radar operates from 600 to 900 megahertz. As you can see that this extends from 1,000 meters to 2,700 meters in ice thickness. We sounded this ice at 750 megahertz with this radar. That's because this large aperture and the technology developments allowed us to develop a very, very high sensitivity radar. Radar sensitivity depends upon its power aperture product. That means you have to have a very large aperture. That's why we used the Mills Cross. and it has to have a very high power, and it has to be able to do coherently integrate signals, extract weak signals. As you can see, the bottom echo is more than 40 dB. That means you can put a radar in space at this frequency and sound most of the Antarctica and Greenland if you're interested. This was done for the first time, proved that by the team at the University of Alabama. And in fact, again, what a high sensitivity does, I'm illustrating with an L-band radar. We also hypothesized a high sensitivity L-band radar can sound Greenland and Antarctic ice sheets and also measure the bottom melt rates of ice shelves. And we have a small NSF project through that. We developed the radar. This was our first version. We wanted to do that quickly within 3 months of receiving the funding. And we took it to Greenland. Here are the results. Actually, this is starts at about 0.8 meters into the ice, goes all the way to 0.8 kilometers. Here is the bottom echo at L-band, 1.25 gigahertz, because we have developed a very high sensitivity radar. So if you have very high sensitivity radar, you can do things you could not do before. When people always tell you when you write a proposal or propose the concept, but that doesn't work because I tried it, it didn't work for me. They don't factor in the technology development and other things that happened over the last few years. Here is what is known as the AScope. See the bottom echo here. This is almost 8 to 10 dB signal to noise ratio on the bottom. This is only one channel. There is 8 channels, and which means that signal will be almost 10 to 15 dB higher than what is shown there in that AScope. And another thing that you have to satisfy is array processing capability and the SAR processing capability for the radar to map these lava tubes. So that's a requirement again. Those are requirements. So this is, I'm illustrating it with data collected as a part of the NASA IceBridge mission. And actually NASA came to us to put the radar on the DC-8 when I was in Kansas. I didn't think we could do it, but one of my colleagues said I can do it. The aerospace gentleman we work with named Rick Hill. So we actually developed the radar and put it on the DC-8, flew it in Antarctica. And as you're flying it, this is actually flying at 10,000 meters over the surface, similar to what you do if you're sounding ice or mapping on lunar mapping from a satellite. So if you see this, this is the surface of the ice, and the bottom of the ice is masked, what is known as the surface clutter. The surface clutter is basically echoes coming from off-nadir angles that are as strong or stronger than the bottom echo that can mask your bottom return. But if you have wide bandwidth, SAR processing capability, and array processing capability, you can do the processing and get the bottom echoes like it's shown here. This is SAR processed, but this is not array processed. This one. This has got SAR processing as well as array processing. You can see that you can extract the bottom echo. And again, this is the case where there is significant roughness also on the surface. Again, I show that here that we extracted the bed returns. This is almost about 800 meters of ice, and this is about almost, as you can see, 20 means about almost 1.5, 1.6 kilometers thick ice. That is masked by clutter. We're extracting it by flying the aircraft at 10,000 meters over the surface. So the other thing that you want to have the radar is 3D mapping capability. Look at the surface and also the extent and the shape of basically your lava tube. So if you want to do that, you want to have the 3D imaging capability. That can only be done if you have the capability to synthesize multiple beams as shown here. These are patterns measured in flight by our team. And my colleague here at Alabama, he was also with me at Kansas, he did that. As you can see, this is the beam that's looking straight down, and this is the beam looking to the left of flight track when you look into the screen, on the right of the flight track here. and you can see that the left and right patterns also as you steered the beam. With that, you can generate the 3D topography. So you see, you're measuring the ice thickness as well as the width and everything else at one shot using this, and that's what you can do. So with this sort of a scheme, you can meet all of the requirements for a lunar sounder. So now let's look at the MIMO concept, how we can do that with the small satellites or small antennas. The way you can do that is, let's consider this as a receive antenna array. And this is the transmit antenna. So if you only have 4 antennas for the receive, 1 antenna for the transmit, this is the antenna pattern you get. Okay. Now, just like I shown here, I have the 4 receive antenna arrays and 2 transmit antenna arrays separated by some distance. So then virtually what I can do is, by transmitting here, collecting data with this, first I synthesize this transmit receive pattern. Then I transmit with this, I synthesize this, effectively only using 4 receive, only 2 transmit antennas, I synthesize it as 7-element transmit receive array. So that means I can use a very thin array to save the weight volume requirements for the antennas. And this is what the MIMO is. I can do this. Here is a concept that's illustrated further. This is the transmit 1. This is transmit 2. See, the first time you do that, if you choose this distance separate way, you can even synthesize an 8-element pattern. So you can do this sequentially. You transmit 1 pulse here, collect data. Without moving too much, you can transmit 2nd pulse, collect data. But you can also transmit complementary signals simultaneously and collect the data from both simultaneously, so you don't have to do the sequential and lose time and some signal to noise ratio. But the price you have to pay is you have to have more power to do that. So there was some studies done by this. Carrier and Gerkos Brazino published a paper on this one in the European conference, and they actually simulated and they recommended if you want a shallow layers, you can operate up to 100 megahertz, 60 to 100 megahertz range. If you want a deeper, going 50 meter and below, you have to have a radar operating at 10 megahertz. And here they did a simulation with assumed characteristics, and they show that they can do a 4-kilometer long along track direction lava tube with that radar. And actually, I've done this calculation when we wrote a proposal. This was at 120 megahertz and 250 megahertz, just to show, not over the whole bandwidth, we can get adequate signal to noise ratio and overcome more than 30 dB to 40 dB of loss through the regolith, the media, in addition to spreading loss, to have this radar operate with very low power with the innovative design. And this is the concept for the radar. I think I want to keep to the time. So as you can see that this is basically, you can generate all of the waveform digitally. You're going to have basically 8 transmitters, 8 receivers. This frequency range, I took it from a figure that I have to do ice sounding. You can change this frequency anywhere between almost 10 megahertz to 1 gigahertz with our current radar. And also you can develop them very easily to do that. And these are the antennas I showed you earlier that you can actually deploy them on a small satellite. And this shows you the previous measurements. As I said, we can go down to 50 megahertz to almost 700, even lower, if you give up some efficiency. Okay. And actually, we are developing a radar to using the MIMO concept. At the minimum, I just illustrate a concept to say you're taking only 6 physical antennas, but you're synthesizing almost 11-element virtual array. That helps you to sound much more complex areas, more clutter-prone regions. For the airborne radar, we are developing this radar at University of Alabama for the Korean Polar Research and the South Korean Polar Research Institute with their funding. And in fact, we may be putting as many as 8 physical antennas or 16. If we put 8, we're going to get about contiguous array of almost 17 or.
How do you turn the volume up on this?
That's I think the highest it goes on yours because I don't see. Let me see.
Okay. And if we use 32, we're going to have almost a, 50 or 40 element array. So which means you really can do some innovative things with this sort of radars. I'm going to summarize what I said. Ultra-wideband radars and MIMO systems have great potential to map lunar lava tubes. And I also think they have a great potential for remote sensing of the Earth. And in fact, University of Kansas is operating a 2 to 18 gigahertz radar right now, and then has operated and also operating radars that work from 2 to 18 gigahertz and also 170 to 470 megahertz. All of that work is based on the concept I developed, and my colleagues developed them and took it to the next level. And I believe the technologies to develop systems are readily available because of the huge investments by communication industry. The amount of money that's put in by communication industry will not match what was put in by the NASA or NSF. That is why these developments are possible. Automotive industry is putting a huge amount of resources too. And actually, the radar market, which is in billions, automotive industry is supposed to be one of the major drivers of that in the future because of the way the radar is going to be an integral part of every automobile. And there was also DoD investments that spawned all of this work initially, without which nothing would have been possible today. But anytime you talk about this, it is considered very high risk. A lot of you involved with NSF and NASA know that when you propose something that is high risk, high payoff, peer review doesn't really do justice to that. It is downgraded, it's very rarely funded. In fact, all of our VHF, L-band, except L-band radar, UHF, all other innovative radars are funded by Europeans actually, right now. The challenges of sending a MIMO radar for the planetary observations are, they generate a very large volume. So that means you have a lot of innovative research to do in real-time processing of data and compressing data and sending data and even further miniaturizing the radar system. So there's a lot of work. Applied technology, applied science in sciences for your students. And so that's what my statement is. There's a lot of scope for innovative work, both in the development as well as application of this technology to the future research. Thank you for asking me to give this talk, and I'll be glad to answer any questions.
Thank you very much, Prasad. This is a great talk. It's a really new idea, I think, even though you already did lots of work. But I think this is to have lots of application to the Earth and to the future moon, because NASA is going to the moon, to the Mars, is the Artemis program. So hopefully in the near future, your sensor will be selected to to support the development for the moon, for the Artemis program. So is there any questions here? You can type your question in the chat, or you can directly open, just ask questions.
I'm sorry, I just am on antibiotics and I have a cough. At this stage, they told me it's not COVID-19. I hope so.
Always not.
Prasad, thank you for a great talk. It's really interesting. I guess my question is, directed more toward the future of the things like the radar sounding of ice sheets. Because with the onset of the ICESat satellite, I think the Ice Bridge missions are not going to be concentrating so much on laser profiling, but I wonder if there's still plans to continue that in the future using the radar sounding, especially since we can't really get the high resolution from satellites for sounding the ice sheets.
I mean, I think that's an issue. I really argued a lot with NASA, but somehow or other, NASA focuses a lot of the things. But recently there was some discussion on resurrecting the airborne program. So I expect some work to continue, but I don't think they're going to fund any innovative radar systems. NASA tends to focus on using the radars that are already developed. In fact, I made a lot of argument to actually put a very capable antenna array on a G5, Gulfstream GV5, and that can actually, with the help of the Germans and a few others, can completely map the Antarctica. But NASA was not willing to entertain that. They don't want to put too much investment again. And but I do agree that the need for the airborne measurement using ultra-wideband snow radars and radar sounders will not go away. I think there is a need for that. I think the community should make a push for it. And if you remember, Steve, when they started the actually ICESat Ice Bridge as a GAP mission, they did not even include the radar. And in fact, I have emails pushing Sealy to include the radar and other sensors as soon as that report came out. So I think some of the community has to push to make it so that the NASA sees the need for that and continues to do so as an international effort with the BAS, AVI, even the Koreans. That's what we are developing the radar so that Koreans can operate an airborne system now, which we will be delivering to them next year.
So, so my question is, if we will be supported by NASA to the moon, we think it will be the drone-based or orbit-based satellite sensor?
I think first they want to do an orbital, and then I think they're looking at the concept for the landers. I think for both cases, you can develop radars that do these things that I'm talking about. But as I said, with NASA missions, you have to have a completely proven technology. I think that is a problem that whenever you propose a new concept, an idea that is a high risk, high payoff.
Yeah, last year they had like a small satellite mission to the Artemis 2. I think I don't know if you try that, or we actually collaborated with UTEP. We sent a small set proposal, but I don't know if it's got funded or not.
Okay. I'm sorry. I think it's becoming bad for me, so I have to.
Okay, is there any other question from the here? If not, then I think our next session is 10:40. We have a few minutes for a break. Then thank you very much, Pasa, for your great talk and open our eyes for the new technology.
Thank you.
Thank you very much.
Talking, and hopefully we can do more of this.
Yes. Okay. So Carla, you can take over, Lana.
Yes, so we'll take a 5-minute break and then we'll come back for the presentations from the Alamo College's interns. And I'll see you back in 5 minutes.
mute my microphone so that I don't keep coughing.
Okay, will do. All right, see you guys in 5. Nee and Haley, if you want to take this time to get prepared to start uploading your presentation, and then we'll move forward from there. And so I'm asking that all of the Alamo College students start preparing to upload your presentation. There will go one back to back. Each of you will have 10 minutes to present. And for questions, those will be dropped in the chat. If we have time during your 10-minute presentation, I will present those to you. If not, then you can address them in the chat, or I ask that your PI will also address them in the chat. Okay? See you in a few minutes.
Hey, Carla. Should we do a big picture here? Yeah. Yeah. So everybody can open your camera so we can group a picture. So we probably need to do two. So only the three actually. How many? Yeah, we need the three to cover all of them, all of us. So you know how to do the screen capture? Oh, I think. Okay. Just yeah, maybe I don't know. So maybe 1 minute. We have lots of them actually. Yes, open, open. I think we almost have the full for the first screen. Passat, Passat. Okay, let's go ahead for the first one. Let's do the first one. Yeah. Okay. Next one. Look. Yeah, just I think probably just yeah, just do the yeah. Okay, the last one. Okay, good. Great job. Okay, I think the first presentation can start.
Thank you. All right. Hi, everybody. Today, Nia and I will be giving a presentation over the use of satellite data to predict sea ice cover in the polar regions. Nia and I have been extremely thankful to be able to work on this project with faculty advisors, Dr. Wang, Dr. Prasad, and Dr. Ji. Also with graduate students Young and Julian with the University of Texas at San Antonio. We obviously want to give a great thanks to the Alamo College District and as well as NASA for being able to give us this opportunity this summer. The scope of our presentation today is, due to climatic conditions and physical barriers, it is extremely difficult, if not impossible, to obtain accurate data in the Arctic and Antarctic regions. To combat this issue, researchers have decided to turn to satellite data to obtain these results, rather than going out in the physical field. Nia and I have been learning how to code in Python and how to use Python in cloud computing networks such as Google Colab and Jupyter Notebook. We've also been reviewing machine learning models and investigating the satellite data sets within these models. We will be using these programs in ISAT-2 and Sentinel-1 data sets to analyze the satellites, to compare results, determine the density of sea ice, and in result, get a higher accuracy level. Below, I provided a visual just to bring in perspective the alarming rates of how fast the sea ice is melting. In the upper left-hand corner, you'll see 1850 all the way up to 1900, and in the bottom, you'll see all the way up recently, not too long ago, in 2013. On the left-hand side, I provided a visual of a graph that was produced from some of the code that Nia and I were assigned to reproduce in the earlier stages. On the x-axis, you'll see the along track distance in meters, and on the y-axis, you'll see the photon ID count. The interpretation of this graph is the higher the photon ID count means the higher number of photons that were returned back to the satellite. On the right-hand side, you'll see an example of a feed-forward neural network that was used to create the graph on the left that we just discussed. If you look closely within the feed-forward neural network, you'll see that we have ice and then what we also like to call lead. When we're doing these classifications, we classify them through open water, thin ice, thick ice, and lead. And for those of us who aren't familiar with the term lead is a fracture in sea ice that defines a linear area of open water that can be used for navigational purposes. On the left-hand side, you'll see ISAT-2 and Sentinel-2 image. For those of us who also aren't familiar with Sentinel-2, Sentinel-2 is a satellite that acquires optical imagery at high spatial resolution. The RGB is the red, green, blue color spectrum that you see presented on the right-hand side. On the brown side of the spectrum, it's going to be open water and thin ice, or open water and lead. And then on the green and blue side of the spectrum, we're going to have snow or thick ice.
So with regards to our methods, the Python language was our main programming language we used. And with the machine learning modules, we used a long short-term memory module and the feed-forward neural network, which we saw a depiction of that in the earlier slide. And the Google Colab was what we also used mainly for computations. And then the Sentinel-1, that's the satellite, the data from the satellite of the European Space Agency, and then the ISAT-2 data of the NASA satellite. So about the results we obtained, Haley had shown us an earlier slide of the ISAT-2 and then the Sentinel-2, where you look at the image, you observe the diagonal line running across it. So that along that track is from which we obtained the data set that we depict in the graphs that we were showing earlier. If you could look at it. Yes, thank you. Now the top left of this, the graph on the top left is the elevation. That shows the photon height. And then we have the standard deviation of the photon height in the bottom left. Then the ratio of high confidence of the signal photons that were returned to the satellite. And then the fourth one on the bottom right is the number of returned photons to the satellite. So on the next slide, this is the data sets showing the labels and then the features that we use in our module. On the next slide, there's also a depiction of the data set that we had to rearrange as an array. There's just a little section of it because we could not fit everything into the slides. And then on the next slide, we also show just a section of the training of the module with these iterations. And this also represents after we had trained our module and then did some validation and then tested, we were able to come up with a 98.65% accuracy. And so what we are looking to further do is to obtain more data to train the model better. And so we'll be looking to possibly doing some image processing as well. So, but that is part of our future works. And then in conclusion, we like to express our appreciation for being able to partake in this project. We have gained a lot of experience compared to when we had begun. So in coding, using Python, and using those cloud services, and then even with the machine learning modules themselves. And as we had stated on the onset of this presentation, our goal is with this project is to raise the awareness to the increasing rate at which we are losing ice cover in the polar regions and how it ultimately affects our planet. And this is a list of references that we had used in this project work. And finally, we want to also give special thanks to the NASA Mairo Kami for the funding of this project, our faculty members for their invaluable help they gave us, our doctoral students for their help as well, and then the coordinators from the Alamo colleges, and then the NASA Mairo Kami Center for this project. And then our last slide shows our poster slide. Thank you very much.
Hello, everyone. Can you hear me?
Yes.
Okay, good. Well, my name is Raul Flores. My summer research this year was over improving best management practices for sensitive karst features on the Edwards Aquifer Recharge Zone. I was under Dr. Yong-Lee Gao over at UTSA, and my co-author for this project was Mr. Michael McMahon. The scope of this project was to develop best management practices, BMP, for karst features located in stream channels of the Edwards Aquifer Recharge Zone. To protect those karst features from non-point source contamination occurring in the first flush, to design a BMP to be cost effective, I'll run over the cost of some sensor equipment, and I'll present to you totalized data of BMP performance as well. So a little background on the Edwards Aquifer. The Edwards Aquifer is a karst aquifer, which contains sinkholes, swallow holes, caves, and many conduits with direct pathways to the aquifer. It does provide 1.7 million people in Central Texas with drinking water, and it is the primary source of municipal water for Bexar County. The recharge zone, 75 to 80% of recharge occurs from streams and rivers that cross the Edwards Aquifer recharge zone. And there's little to no filtration within these karst features. Groundwater flows through conduits that allows for efficient stormwater recharge into the aquifer. Lately, there has been significant residential development on the recharge zone itself. If you look on figure 4 over here on the right-hand side of my screen, you'll see from 92 to 2011 in red above the black line, that shows an increase in residential development on the recharge zone of the aquifer. And that development brings on an increased risk of a non-point source contamination, which is all the runoff picks up contaminants such as, petroleum products, say from changing your car's oil, nitrates from fertilizers. So all that gets picked up and that can adhere to your TSS, which is your total suspended solids. So there is protection for these karst features. The Texas Commission of Environmental Quality, or the TCEQ, they do provide installation guidance for these BMPs, but mainly in upland regions. If you see in figure 5 and 6, these are 2 examples of current BMPs that are implemented. As you can see, they're just a cage cover over that natural cave that's in an upland region, but they do lack sufficient guidance for features located in stream beds. Again, these BMPs are placed directly over swallow holes and swallows. So the objective of this project was to develop a cost-efficient, low-maintenance BMP designed for blinding these features located in stream channels from non-point source contaminants. My hypothesis was that conceptual BMP design would blind features from the first flush contaminants and would later open to allow for cleaner waters to enter those karst features. I used SolidWorks 2020 for the design of my BMP, Microsoft Excel for regression analysis to generate data for flow in cubic feet per second, stage level in feet, discharge, TSS and nitrate loading. TSS was your total suspended solids. The data was collected from a water quality station located within an unnamed tributary to Leon Creek. Data was then quantified, totalized the concentrations of your TSS and your nitrate loading. So here in figure 7 is the design of my BMP. It's a 5x5x5 concrete BMP. Right here on the side of it is a housing that houses a linear actuator. And that linear actuator is attached to a level sensor, water level sensor, as you can see in figure 9 here. That's a ProSense water level sensor. And that sensor is attached to a still well. So that still well allows water to allows water through these inlet tubes here at the bottom. So the BMP is placed over karst feature. Still well is on the embankment. As that storm progresses, water level rises, allowing water through your still well. Once that water level peaks, a circuit will then be completed, and that actuator on the side of the housing of the BMP will be triggered to retract, allowing that lid to open, allowing for recharge into that karst feature. So I came up with four options for the BMP design and sensors. The first BMP would be the one I showed you, and it would stay closed for the first storm of the season. That's not optimal, as it doesn't allow recharge into that aquifer, and that will require a lot of human intervention, and that will be without any sensors, so it bring the cost down to a minimum. Next one would be the BMP with the water level sensor that I just showed you. That cost for that sensor is $143. It does optimize the costs, and it allows for better performance. It allows that BMP to open at a better time. As we go up the chain, the sensors get more expensive and they just get more sensitive. The next option will be a sensor that reads turbidity, conductivity, and water temperature. That runs around $795. It's an incredible sensor. It reads a lot more sensitive. It is costly though. The next step up from that is a sensor that can read everything: your turbidity, your water level, your temperature, your conductivity. and that's going to run just under $4,300. It is the most expensive, but it is the best option as far as allowing that BMP to open at the most precise time. And these are results from a storm event which occurred January 10th of this year. As you can see, the water level rising here in red for the initial part of the storm. You see your total suspended solid concentrations increase as your water level begins to decrease, and that's just due to your water level receding, so your concentration is going to rise due to lack of dilution. And this here will be the time we wanted that BMP to stay closed. As it begins to recede, it would open. And as we see a high turbidity in the first flush, we see conductivity low at the beginning. That's just because there's a high volume of water. And when turbidity decreases, you see your conductivity rise. And your conductivity is rising, which is in your nitrates due to the lack of volume as your stream recedes. And that brings me to our conclusion. So your total suspended solids concentrations without protection of the BMP was 26.4 milligrams per liter. TSS concentrations with BMP, 6.7 milligrams per liter. Your nitrate concentration without BMP protection, 1.9 milligrams per liter. And with BMP protection, 1.8 milligrams per liter. Total suspended solids prevented from entering the feature with your installation of the BMP was 62.7 pounds. Your nitrates was 1.06 pounds. So we saw an improvement in water quality for total suspended solids at about a 75% reduction in those solids. And there was also a slight improvement for nitrate loading reduction at around 5%. Here's a little brief overview of the pricing on these sensors and how expensive they can be. And on the right, you see the ProSense level switch, which was the $143 option. A quick recap and summary. Highly urbanized areas do bring on an increased risk of non-point source contamination of heavy metals, petroleum products, and nutrients known to adhere to the TSS, or total suspended solids. After data was collected, analyzed, and quantified, conceptual BMP lowered TSS concentration and nitrate concentrations. Significant water quality improvements were made, lowering the risk of non-point source contamination. My BMP conceptually blinded features with a significant reduction in total suspended solids, a small reduction in nitrate loading, overall improving the water quality. Future works, here's at the bottom in figure 18 is implementing the BMP sensor and still well system to protect these cards features from non-point source contamination. And this is a quick look at what that would possibly look like. Little overview of my references for all this research. And I'd like to take this time to thank Dr. Younglee Gao, my co-author and geological sciences research assistant, Mr. Michael McMahon, academic program director, Tamika C. Wilson, my peer mentor, Nancy Benavides Ortega, and NASA Miro Kami for providing us funds to do this. And here's a look at my poster. And again, thank you all for this opportunity to share with you today my research, my findings, and what I've learned throughout this process. Again, I appreciate it all. Thank you.
Way to go, Raul.
Thank you.
Can you see the screen? Oh. Yes, ma'am.
Are y'all able to see it? I don't.
Yes, just probably speak up just a little bit.
Okay. Hi, my name is Marcelina Garcia, and this is the visualization of COVID-19 and the world. A little bit about me and about the project. My name is Marcelina, but I prefer to go by Marcy. I am 19 years old, and my major is in cybersecurity. I go to St. Philip's College, and my PI was Dr. B, and she was incredible. I also got help from Mr. Tan, and he was a big part of the project. The project was to get a visual of where COVID-19 was taking places and the latitude and longitude of those places to see if it had a big impact on the locations of it. I'm sorry. This is COVID versus the USA. So in the graph, we have Alabama through Wyoming, all 50 states. And in total of the United States, this had 2,234,425 cases. And this was as of June 24th of 2020. Now, the most affected was New York at this time. And in just New York alone, it had 300,000 cases just by itself. The least amount was Hawaii, and that was with 1,001, and that is nothing compared to 404,000 cases. But it also had the lowest number of deaths with only 26. The United States cases. So on the left here, we have the United States mass. And it gives you a little understanding on whether what states are required to wear masks or not. And it shows the mask state if they are required, and if they are not required, it has the NA. And it also shows you the latitude and longitude of each state. Now on the bar graph to your right, it shows the number of cases each state has for the coronavirus. As you can tell, again, New York, has the majority of the cases. Now the top 10 countries with cases, and this picture was taken on August 4th, 2020. The top first state, of course, was the United States, and next was Spain, Italy, then the UK, France, Germany, Russia, Turkey, Brazil, and then lastly, Iran. So at the bottom left of the corner, you can see there's a bundle of dots, and that replicates the country's cases and their deaths. Now, if you notice at the top right corner, there's a dot, and that is the United States. It's pretty scary seeing how other countries are being compared to the United States, and how we're the most affected and in all most dangerous. Deaths versus latitude and longitude. As stated in the beginning, we wanted to see if the latitude and longitude was the reason why these cases were being extremely large. So if you see in the graph to your left, majority of them are by the 0s to the 100 range, versus the graph on the right, it's by the 20 through 60 range, and that's the positives. So this is COVID-19 versus latitude. These are the cases. And it looks very similar as the last graph, but these are cases and not deaths. So once again, they're mainly in the 20 to 60 range. And this is places like the United States, China, China and the UK. And the black line gives you an idea, because that is the positive 40. So you can see the generalization of where the cases are being brought up, or the majority of them are. Now, COVID-19 versus longitude. And once stated again, it looks very similar to the deaths, but this is the cases. And it's between the 0 and 100 where the majority of them are. So that is in Europe, Asia, Africa, and that red area shows you an ideal of where that general area is. I want to mention that I used Anaconda to help me with this, and it was a big help, and it helped me throughout this whole project. I didn't know anything when I first started this project. I only knew the basics of how to use Word, and I didn't even know how to use Excel. But with help from everybody, I was able to use Excel and use Anaconda, and being able to use that is a real big part for my future, because with cybersecurity, you have to know coding, and a lot of that coding was used with Anaconda. I want to thank Tomika Wilson, Dr. B, and Tan for helping me with this project. I couldn't have done them without them, along with the SEMA program, the SEMA staff, NASA, everybody was incredible, and I love them all so much, and thank you for that. And this is my contact info. Thank you.
Yes, yes, yes.
Jacob, you need to unmute yourself.
Oh, sorry. Can everyone hear me?
Yes.
Yes.
Hi, nice to meet you, everyone. My name is Jacob Lyda. This summer, I was introduced to supervised learning from Dr. Adel Alayadini at the Mechanical Engineering Department at UTSA, and my objective was to perform a simple linear regression analysis. Machine learning is the science of getting computers to learn without being explicitly programmed to do so, as defined by Arthur Samuel in 1959. Examples of machine learning would involve data mining for large data sets and applications we cannot write by hand, such as handwriting recognition software, or even feedback when you mark certain emails as spam, or you like certain videos or content on media platforms so that you can get similar recommended content. The objective of machine learning is to understand human learning and improve upon the ways we learn as people. Arthur Samuel's definition is a bit dated, as it was in 1959, so Tom Mitchell has defined machine learning in a much more modern way. A computer program is said to learn from experience with respect to some class of tasks and performance measure if its performance at tasks, as measured to some degree, improves with experience. An example of this would be playing checkers. So T would be the task of playing checkers. E would be the experience gained from playing those several thousand simulations against itself. And P would be the probability that the program will win. So as the program simulates games against itself and learns optimal board states, gains experience, its performance, the probability that it will win, will improve. Ni and Raoul both used regression analysis and machine learning, and it has application to not just one specific area. It is a prediction method that has pretty much unlimited potential. This potential is used in AI and data science and computer science. So in video games, it can create interactive gameplay or adaptive interactions. It can improve diagnosis in health services based off of data sets of previous cases. It can identify key parts of financial data, so for example in stocks, and you can make monetary predictions based upon those data sets. And it can even use data mining to detect fraud and prevent identity theft for your personal security. And Ni used it for polar sea ice, and Raul used it for the Edwards Aquifer, which I think is very, very wonderful. All machine learning problems fall under two categories, supervised and unsupervised learning. Supervised learning refers to the task of a program learning a function provided with input and expected output data. The program is then provided what to look for, and the model is trained for pattern recognition. Unsupervised learning is essentially the same, except the program is not provided with input or expected output, only what to look for, and then the model is trained to look for patterns. Supervised learning is performed through two methods, regression and classification, which my colleagues used regression, which predicts continuous valued outputs, which are integers, floating points, and numerical values, which are purely numbers, and classification, which predicts discrete valued outputs, which are zeros and ones, yes and no, or class A, B, or C. As the name suggests, it will predict classes of data. And it will focus on regression, as the values I was set to find were purely numerical. Linear regression models the relationship between these variables using a linear equation with your known data. A linear regression line takes the form of any other line or linear expression of y equals mx plus c, where x is your single variable input, your predictor, and y is your output, the predicted, where m is also your slope and c is your intercept. And we can code this, and all we have to do is assign each variable. Mean squared error or squared loss is the most common method for fitting a regression line to a linear model. The equation is as follows: 1 over m times the sum of the difference between your actual output data and your predicted output data squared. And that squared difference is where the name squared loss comes in. But after plugging in this regression line equation for the actual output data, you get the following equation: 1 over m times the sum of mx plus c minus your predicted output data squared. This function will determine a line of best fit through the data by minimizing the sum of squares vertical distance from each point in the data set. This is an example. Our objective is to find a regression line that minimizes the distance between each point in the data set vertically. In order to minimize this mean squared error, it is essential to update the linear regression model's parameters. Note, however, that the model is a mean, so it is susceptible to outliers because it is an average. And to do this, we implement a method called gradient descent. A gradient descent merely uses the gradients or the partial derivatives to update these parameters. So using the previous equations, we find those partial derivatives with respect to m and c. The partial derivative with respect to m is as follows: essentially the mean of the x and y values, and the derivative with respect to c is essentially the mean of the y values. And with these partial derivatives, we can plug them into an equation that will update our parameters, where alpha is our learning rate, which is assumed to be within the range of 0 to 1. To explain this further, alpha, our learning rate, is the rate at which our model progresses. So if our objective is this minimum point here, the closer it is to 0, the slower the model will learn. So if it's 0, the model isn't learning at all. So the closer it is to 0, the model will progressively get to our minimum point, but at a painfully slow rate. And on the other hand, the closer it is to 1, we could make jumps so drastic that we miss our minimum entirely. So we assume it is between the values 0 and 1 so that we find a smooth rate of learning so that the model will progress gradually to our objective. The tools I used was the online resource, the Jupyter Notebook. I coded everything in Python. I used the NumPy and Matplot libraries. A NumPy is a matrix operations, and Matplot allows me to display graphs and plot data. And my sample data set, unlike Ni's 7,000 by 21 matrix, mine was only 100 by 2 matrix. And as you can see, it is just a bunch of random values between 0 and 100, and it just went on for 100 rows. In our first lines of code, we import our libraries here, and we import our data set. Here I'm assigning that the first column is the x values, and the second column is the y values, and we confirm that the matrix is the correct shape. It is 100 by 2. Once the data set has been opened, we can split it into training and testing data. What we will do is we will train the model using the training portion of the data. And once we find our parameters and our model, we can apply it to the testing data to see if it is accurate. I used a 70 to 30% ratio of training and testing. So the first 70 rows are training data and the remaining 30 are testing. To begin with our initial guess of the intercept and slope, to see how accurate we are, I generated 2 random values and I assigned the input variables and output variables to the training data so that the testing data remains unaffected. This is the display of the first 70 points, the training data, and it is just a bunch of random values as said earlier. And we're trying to find a model that will create a line of best fit that we can apply to the testing data. This is our mean squared error equation, and we can define our variables. So we begin with our difference squared. This y hat is our predicted y values minus our actual y values squared. So that is our squared loss. And the number of samples times 2 would be the 1 over m. M was the number of variables. And in this case, there are only 2, x and y. So that's why we multiply it by 2. Once we've defined the mean squared error equation, we can implement our gradient descent functions. I used a while loop with threshold for optimization, and I used memory to store our parameters once we find them so that we can find our optimal parameters. We begin at iteration 0, and this is where how I store the parameters. This is the loop that I used and the conditions. And these equations are essentially just the derivatives of the previous ones. And our model will update iteratively, and we're looking for our parameters that we'll store when we call them from memory. Once this is done, we can assign our training data, x and y variables, the 2 random values you generated. Alpha, I used a value of 0.3, and I generated 200 iterations. Iteration 0 began at around 70, a little bit above 70. And as you can see, as the model progresses with each iteration, it'll gradually decrease. And to find the endpoint, we call our parameters directly from our memory, and we can see that it approaches 64, which is the slope, and 27.38, which is the intercept. Once we can do this, we can use our predicted values and assign it to the testing data with our parameters. And once we do this, using the parameters we just found, we can find our best fitting line. And it is applied to the remaining 30 values, the testing data, and we can see that it's pretty accurate. In summary, we received and opened a sample data set of random values. We prepared and plotted a data set, and we set our objective to find the regression line using mean squared error. We defined the mean squared error function with the variables assigned and generated random values for our initial guess. And we defined our gradient descent function with our mean squared error function and wrote a program that would update itself iteratively and to find our optimal parameters. We substituted our variables and generated 200 iterations to find our parameters. And with this, we found our regression line. What now? As said before, machine learning has pretty much limitless application to other fields of science. And I was learning machine learning through Dr. A's recommended program, which was an online course. And they used an example where you could check the probability that a breast cancer patient would have a malignant or benign tumor based upon previous cancer patient data. And I think that has really promising application to see that we can diagnose people using just data and simulation. These are my references, and I would like to give a special thanks to my faculty advisor, Dr. Adel Elayadini, my research assistant, he's a graduate student, Sid, my peer mentor was Nancy Benavides, and a special thanks to Mrs. Tamika Wilson. Mhm.
Good morning. This entire summer has been a great experience for me. Wanted to share my research. So my research this summer was satellite remote sensing of extreme snowpack melting on Eagle Island, Antarctica. And before I jump in, I'll give you a little background on a little thermodynamics, but snow's albedo, or how much sunlight reflects back into the atmosphere, is extremely high, reflecting about 80 to 90% of incoming sunlight. So this is super important for Earth's energy balance because it reflects solar energy back into space, which helps cool the planet. Our polar regions are very sensitive to climate change. Therefore, it's important for us to, as scientists, to monitor the variability in snow accumulation at those high latitudes. So Eagle Island is it's a small island off of the northern tip of the Antarctic Peninsula. So if you can see here on the left-hand side, we have our northern Antarctic Peninsula, and we're zooming in a little bit here on the right. And if you can find number 12, this is going to be my study area here, this little island on the right-hand side of the peninsula here. So recently, this island, Eagle Island, has experienced occasional events of extreme snowpack melt. Some of that snowpack melt has been reported in the news recently. So these pictures are actually taken from NASA Goddard and from a satellite called Landsat 8. On the left-hand side, earlier this year, on February 4th, 2020, you can see it looks pretty normal. And on the right-hand side, some pretty extreme melting. So just a mere 9 days later. So what I've done this summer is taken some data and using observations from NASA's Earth Observing System satellite project, particularly the Terra satellite. I've taken some data from there, and we can examine these snowpack changes on Eagle Island. The sensor that kind of provides these observations is called the MODIS sensor. It's the Moderate Resolution Imaging Radio Spectrometer. And we collected cryospheric data there. About 1,200 data points were taken from the Terra satellite, gathering that data set from the National Snow and Ice Data Center. And we've gathered that data about every 8 days and kind of split that up between snow cover percentage and land surface temperature. And what I want to do in this study is observe the snowpack on Eagle Island. We took the data from the past 20 years and try to analyze to find climatological means and anomalies in snowpack to characterize these extreme events. So taking the snow cover percentage over the past 20 years, and I've plotted the average snow cover here in this blue line here. I've made a couple graphs, and the Antarctic summer kind of runs from September 6th to about the end of April the next year. So my x-axis is actually going to be in Julian days. So day 281 here on the far left, going all the way over there to day 73. And what I've done here, this blue line again, my last 20 years for data is going to be my average. And you can see in November, about day 337, we had an extreme snow melting occurrence here, and another one over in December. But according to my data, I'm not really finding much to show for this February melting here. So I kind of want to dig in further to my data set and see if we can find some information. So what I've done is created some histograms here just to separate my data and see what I can find some averages here. So you can see on the top, Eagle Island's kind of averaging snow cover percentage, which makes sense, around 82 to 90%. And then that bottom one, we wanted to find some anomalies. And if you're familiar with anomalies, it's simply just the difference from the average. And I wanted to see where my extremes were. So you can see on this left-hand side of my histogram, we have about 12 extreme snowmelt events here. So wanted to dig in and see if we could find some more information on what explains those snowmelt occurrences. So I've taken my entire 20-year data set and I've plotted each snow cover percentage here for the past 20 years. You're gonna see that blue line again. That's gonna be my 20-year average. And then we made a lower error bar, lower standard deviation error bar, just to see how many times something has dropped below the average there. So went through and analyzed to see if that February occurrence was appearing, and again, it's not, according to my data, it's not popping up. So I wanted to go back and see some land surface temperature. Again, took some data from that Terra satellite and wanted to correlate to see the land surface temperature of Eagle Island and see if that has any correlation to the extreme snowmelt, those atmospheric conditions there. So as you can see here in these histograms that I've made, we're averaging, again, which is pretty normal, we're averaging about -5 to 0 degrees Celsius there. And then on the right, I want to find some anomalies. And I was expecting to see on the right-hand side of my histogram about 12 melting events, and those aren't popping up in my data. So I made that same graph here for the past 20 years, my 20-year data set. Just again, going into some more data analysis. And this is land surface temperature over the past 20 years. Again, that blue line is going to be my 20-year average. And I wanted to see if anything kind of popped up higher than 0 degrees Celsius. And again, nothing is really showing me any relevant atmospheric climatic indices. So I took my two variables and I made a scatter plot just to, again, kind of correlate those variables together. And this is all, it's all been noise so far. So I really don't see any linear regression here showing me any relation between the snow cover percentage and the land surface temperature. So this next one is again just a histogram, putting those both those histograms side by side. Again, you're going to see on the left hand side we have snow cover percentage in the blue, those 12 heating events over Eagle Island. Those did not correlate to the land surface temperature. On the right hand side, I wanted to see 12 land surface temperature heating events. And so what I'm doing here for the moving forward, I'm lucky enough to take my research into the fall. And what me and my professors want to do is look into a term called degree days. And pretty much what that means is what's the atmosphere like leading up to that February melting event that I showed you earlier in those pictures. So we're moving forward in the research, and we're going to go back and find some air temperature data from some weather stations around Eagle Island. So, but I wanted to make a table of those 12 heating events that happened in my data set, my data analysis. So I made a table here, and what's interesting to me is not that these extreme heating events have happened, but that they continue to happen over Antarctica. So I'm interested to see how they compare moving forward. So studying these associations can help us understand how extreme snowpack events are related to climatic variability. So again, yeah, I just wanted to say that are these atmospheric circulation anomalies a consequence of global warming or just the result of natural variability? Or, and again, moving forward, just wanted to see how those kind of relate to each other. So definitely appreciate your time, and I wanted to thank Tamika for letting me do my research this summer, and the rest of the CAMI presenters. And yeah, that's what I got for you.
Okay, can you all hear me? Yeah. Okay. So, hello, my name is David Perez, and my presentation is on molecular dynamics for simulating metallic energy potentials. I worked with Dr. Wei Gao from UTSA, and he assisted me with the frames of my research. So we began to look to find the ideal structural material. And for structural materials, we often look toward metallics. And one of these metallics, such as titanium, has many useful properties, such as its corrosion resistance and its high strength for structural use. However, it still has issues that remain. And many of these positive and negative properties, as for any metal, depend on the molecular structure. And fortunately for us, molecular dynamics can be used to investigate the potentials for these titanium along with its alloys. So using molecular dynamics, we can analyze and compare to decide which would be most useful for general constructional usage. And what exactly is molecular dynamics? It's the method of visualizing the possible movements of atoms and the molecules using computer simulations. By giving it adjustable timeframes and adjustable environments, you're given a dynamic view of your atom or molecule. And for this research, we used LAMMPS and OVITO. LAMMPS is the large-scale atomic molecular massively parallel simulator, and OVITO is the open visualization tool. So a quick overview on how these simulations would work. These calculations fall back to Newtonian mechanics and Newton's second law, as most physics do. Because if you're able to use the forces between the atoms and take the mass of the atoms, then you can find the acceleration, which is just the second derivative of displacement. So using the forces and second law, that you're able to define the atomic locations of each atom, and define the crystal structure of your metal. And using these mechanics, you can use molecular dynamics to also determine the structural stability, as if an atom is highly symmetrical, that means the forces are more evenly distributed, leading to a less likelihood of collapse. So metallic crystal structures have one of three possible structures available to them. If we look here for our titanium, we find it under the hexagonal close packed form. And from the rest of these, we can see that softer metals such as gold and aluminum are face-centered cubic, which are known to be the most ductile form. And in between is body-centered cubic, which is about less ductile than face-centered, but not as brittle as hexagonal. So unfortunately, the titanium being hexagonal close packed, it causes it to be brittle in the cold. So to optimize it, we'd find a stable face-centered cubic form that would make titanium more ductile and easier to work with. Alongside of those issues, titanium is also costly to refine and produce due to its rarity. So introducing an abundant metal as an alloy would assist in its costs. So for this experiments, we use lamps to simulate titanium, titanium aluminide, and nitinol. 3 tests were replicated for each of these metals to analyze their stability after 20 picoseconds. And the temperature and stress conditions remain constant for these simulations. The changes only apply to their initial structures. So we see here this initial test used the single titanium crystal structure, and it attempted to place it in a fully face-centered cubic form. And as the simulation progressed, it ended up reverting back to its hexagonal close packed. And using Ovitos, we were able to see that the cell was not able to remain in its face-centered cubic form, and that's what we're looking for. And using Ovitos to color code, we're able to also sort out the atom center of symmetry, with dark blue being the more symmetrical and dark red being the least symmetrical. So this is the same simulation but color coded, and we see that the symmetry is lost as the simulation progresses. So we take a look at our first alloy, titanium aluminide, and using the environments of a standard room temperature, we're looking for the center of symmetry and potential energies of the atoms. This particular simulation initialized in a randomized crystal data structure so that the atoms were not perfectly placed to begin with, and it was more accurate of a real-time, real-life simulation. So we see that as the simulation began, it initialized in a 60% face-centered cubic and a low amount of hexagonal, 7%. And we're looking to have a low amount of hexagonal, unlike the initial titanium. So we see that as the simulation progresses, 6% hexagonal, 8% hexagonal, and 10% hexagonal. And the color coding also shows that it maintained symmetrical stability. So we saw that aluminide in a random crystal data structure was more rigid and consistent in its structure. If we initialize it as a 100% face-centered cubic, we see that by the end of the simulation, it maintained 50% of its face-centered cubic, and the color code also shows as well that the blue kept its stability. And now we look at nitinol, the nickel-based alloy, using these same environments and the same randomized crystal structure. We see that this one was initialized in a 100% face-centered cubic. While what surprised me is that almost immediately as the simulation progressed, it jumped to a 30% hexagonal. Fortunately, as the simulation continued, it sprang back to about a 93% face-centered cubic structure. And the blue color coding shows that it maintains stability from the beginning to the end. And if nitinol was initialized as 100% face-centered cubic, what I found this was the simulation that I found most interesting, as the blue tells you that it was symmetrical and stable, yet if you look at the data for the structure, we find that it fell to a 4% face-centered cubic. Yet the blue contradicts it, showing that it's still stable, showing that nitinol was flexible enough to maintain its stability, but it wasn't rigid enough to keep its structure. So the third and final test I put as a guessing game, so we could use what we know between these two alloys to look at these results without the names of which one. And I want you in the chat, or just to keep a mental note, to put which one you believe the simulation one belongs to. So we see here they both initialize the same as 100% FCC, and this was a tensile test between the two alloys. It basically put stress on the cell and saw how the cell would react to it. So we see in the first one, after stress was applied to the cell, it fell to a 60% hexagonal close pack. And if stress was applied to atom 2, a molecule to cell 2, it maintained above 70% face-centered cubic. And this is the result we're looking for to see its structural stability over. So if you'd like to put in the chat which one you believe atom or cell 1 belongs to. So as we see in the next one, the atom 1 belongs to the nickel-based structure, and atom 2 belongs to the aluminum-based structure. Because in the previous results, the nickel-based one wasn't as rigid to keep its structure. And looking at what in the real-world applications of what these alloys are used for, titanium aluminide utilizes titanium and aluminum's lightweight properties and durability, making it useful for aerospace and automotive industries, while nitinol has a unique property which makes it very flexible and more often used in a wire form. It's seen in dentistry and other medical uses and could be used in many other fields. So overall, the uses of these simulations, one of the major issues we had with titanium was that the costs of performing these stress and heat tests would prove to be expensive. And using computer simulations, we're able to negate that. We're also able to witness the advantages of each form of these alloys and could have possibly found a use for them without prior knowledge. So overall, which is the best for construction? Titanium proved to lack its stability in a single face-centered cubic crystal structure form without the introduction of an alloy. So that kind of was out of the question. So titanium aluminide proved to be the stronger of the two alloys from the simulations, as it retained its consistency in the structure as well as its stability. However, nitinol's flexibility made up for the lack of strength. And while nitinol proved to be highly persistent in its stability, I'd say that the aluminide would be better for comparatively larger uses, such as engines and vehicle frames, due to the stability that it had under pressure. So all of the resources, the information was found from the Interatomic Potentials Repository, the LAMMPS manual, and the Mississippi State main page for molecular dynamics. So this research was made possible by the NASA Mirokami and SEMA LSM internship. It was funded by the National Science Foundation. Special thanks to Dr. Wei Gao, my faculty mentor, Tamika Cross, and the SEMA peer mentors, as well as the support of my fellow interns.
All right, hello everyone. So like she said, my name is Leanne Serrano. Let's get started. Today, I will be talking about my purpose in the buckling analysis of the hexachiral structure for use in materials at NASA. And I worked with Dr. David Restrepo and his team at UTSA. So the purpose of the AMMS lab is to research in nonlinear behavior in periodic architecture materials. And my focus in this group was to build, assemble, and analyze Dr. Restrepo's hexachiral structure, and also analyze singular unit cells to test different deformation patterns and validate either local or global buckling when periodic boundary conditions are placed. And this research is important so that we can discover new materials with qualities that we've never really seen before, and then use these materials in everyday life and in multiple fields. So let me explain to you a little bit about the geometry itself. It was comprised of 1 node to 6 ligaments in a radial 360 pattern that I had to, build basically from scratch and then assemble together and then cut down to make the unit cells that you see here on the bottom left corner. After merging, or let me restart. So while I was merging these parts, I ran into quite a few problems. So a big chunk of my time was a lot of trial and error in trying to figure out how I can merge these parts together without any errors occurring. And so that way we will be able to insert it into a MATLAB code so that we can apply periodic boundary conditions and then get results from the code itself. So after the large chunk of time where I was trying to figure out how to merge them, I then I gave the model itself some elastic properties. And then after placing the elastic properties, I then meshed the parts. So meshing actually assigns the ligaments a certain amount of elements. And with these elements, we're actually going to then analyze the deformation basically, or sorry, I got a little stuck, but yeah, basically that. So then from meshing, we then get the results from, like I said, the MATLAB code. But as we were putting the input file, so I had to generate input files for these models, and whenever we would insert it into the MATLAB code, we would then find little errors here and there. So like I said, it was a lot of trial and error. So I had to then either fix the model, or I had Juan David, I worked with him a lot, help me out with fixing the code itself. So like I said, I did run into a lot of problems. So I only was able to get the results of one unit cell, but as we can see here, we can prove that there is local buckling when periodic boundary conditions are placed in the model. So when we are actually able to put the bigger unit cells within the code, we will compare the one unit cell with the larger unit cells and see if these results are the same. And so it'll either prove or refute if there is global or local buckling present when these materials are being, when there is periodic boundary conditions. So in conclusion, since I did create the input files for all of these models, what we're gonna do next, or what the next person is gonna do, is then put these input files into the MATLAB code, and hopefully it'll run smoothly, and they will be able to actually get data from these models, and then from there be able to continue on to the research and get something from that. And I would like to thank Dr. Restrepo and his team for helping me out so much through this experience. This is my first time doing any sort of research, so I'm really glad to have been exposed to a very different environment. And even though it was from home, it was definitely a learning experience. And I would like to thank Miss Tamika Cross, because she helped us out a lot too in this process, and Miss Carla Kidd. And here is my poster if you guys have any questions. I know I probably rushed through it a little bit just because lack of time, but I would like to thank you all for listening. Thank you.
Way to go, Leanne.
All right. Y'all can hear me? Hello?
Yes.
All right. All right. Good morning. Welcome. My name is Alejandro Zarate. This summer, I worked under the NASA CAME program. I was researching portable modular one sensor technology under Dr. Behenagar as my PI, and my co-PIs, Daniel Byrne and Ethan Benman. Scope of this presentation, we're going to talk about what is a RevP1 sensor. We're going to break down the code, and then we're going to build a simple temp sensor. The other two last things under here is research, further research. So we're not just there. So when by the end of this year, I should have everything done, and for I think for future future presentations, I can have all that down by then. Yeah, my camera has a little my system has a glitch, and so I have to restart my whole computer. Yeah, sorry, I apologize for that, but I can't. I got things running, and if I stop running things, I lose data, and I don't want to do that. Pretty sorry for that.
Okay, go ahead, Zarate.
Okay. And here's the actual sensor itself. Some specs on it. It runs a it's a combination of a thermal and a hot wire anemometer. It runs at 9 through 12 volts. Width, length, and height is 1 inch. It will sense seriously, going into the code breakdown, these are things you start writing down. Your first two, what you're going to be reading off your inputs. You'll see the diagram, how I wired it up. Sorry, and here I'm explaining what's the next step to writing the code. So your communication from your Arduino towards your computer. And here's the third step. You write your void loop, and void loop technically is just where you put your program so you can run it continuously. And right here we write the code for our when, so we can what we're getting from our when pin for sensing wind speed. So we go in, we grab what the sensor is telling us, we run it through an equation, and then we once what we get from the equation, we print it out in our serial port, and the rest of it's basically I'm telling you what everything means here. Give you a few seconds, scan it over. Okay. And then our secondary part is going to be for our temperature. So same thing like on our first part, we take what our sensor is telling us, we run it through again through an equation, and we print it out as on our temperature side, and then we delay this. Then at the end, we delay this process 3/4 of a second. 3/4 of a second. You can delay it as much as you want. Really doesn't matter. And then here's the code, all laid out, short and sweet. So, and then we got me testing out the sensor itself. On your left side, I'm calibrating the temperature sensor, so I'll make sure that it's reading right. And the way I calibrated, I was using the indoor temperature, the thermometer sensor for my HVAC system or my air conditioning system. And then on your right, you'll see I'm testing the wind speed sensor. So I blew on it, and I went from reading 0.03 miles an hour to 1.68 miles an hour. And that's relatively, pretty fine for a human to blow that hard. You can blow even harder, but it all depends on your physical lung strength there. And then we're going into building our own simple temp sensor. These are the things you're gonna need. We go to the code breakdown. Technically, the blue wire, what we're trying to read is a voltage differential between our thermistor and a resistor. You'll see on the diagram where that blue wire connects, and it's between those two, the thermistor being that little black dot and our resistor being that that brown cylinder shaped deal. And I explain why there's a voltage drop equation. Here we use, I explain more of the voltage drop equation, and we use Sainer-Hart's equation to figure out what we're gonna be reading off, and then we rewrite the Sainer-Hart equation so we can have it, so we can write it on our code, and that looks like what you'll see in the bottom middle section. And then here I explain basically all the process, what we have, wrapping up everything, and why we have what we have on our floats. Let's give you some time to read that. Okay, and then we go, like again, we do a void setup. And then here's the whole equation down. And so we take what the blue wire is bringing us, we run it through our equation, and then we convert it because, like I said, on the rev P, our equation will only each equation that we put out is gonna give us temperature on C. So on here I do a further step and I convert it. We convert it to Fahrenheit. You'll see on the last our last two T equations that process, and then we delay it for 2 seconds. So, and then while testing this, I made a simple error on the top data. You'll see that I used, instead of using a not normal, but a 10K resistor, I used a 100K, and it was giving me wrong readings of up to 200, over 200 plus Fahrenheit. And then I realized that that error, and then I swapped it out for a 10K resistor, and you'll see that I was reading where I want it to be reading. And then here I'm touching the sensor itself to see if it could get up to my body temperature, and we'll see it did. And then here I'm letting the thermistor go, letting it go from sensing my body temperature to room temperature. And then here's a simple idea I had as part of the future work. So taking in account of our thermistors, I was planning to get 8 thermistors on a circle. This is technically taking the idea of reading temperature, but translating it to read wind direction. and this idea will work with the REV-P sensors. But technically, what the idea is having 4 pairs, or basically pairing up the north, the south, north and south, on a pairing those two up, and if we have a north or south wind, we'll sense a temperature difference. We'll sense that the north thermistor will go down in temperature, and then our south will go down in temperature. And by figuring that out, we'll put out the system will pull out, okay, I'm sensing one speed, one direction from north or south, and vice versa, and all the way across. And then here we go to future work. Like I said, we're gonna be testing this idea. I'm gonna be building we're gonna be building modular 3D bracket designs for the REV-P sensor itself, so we can mount it in a rover or drone. That's part of the major project that I'm working on. They're my co-PIs. And then the last thing is weatherproofing, waterproofing the sensors themselves, because we're going to be using this technology. We're going to prove our concepts, and we want it to be, these little sensors are tough enough to sustain harsh and difficult environments. So right now, if we can waterproof them, they can go anywhere around Earth to sense, for the big scope of this program itself. All right, any questions? This is my last slide. And I'm hoping I'm under that 10-minute. Yeah. Thank you. Appreciate it. God. Yeah. What the?
No, just to remind, we will start at 12:45. Yes, 12:45.